And this is my lab submission for our first lab in Physics 2211. The purpose of our lab was to observe an object with the constant velocity and use that to demonstrate Newton's first and second laws. And we'll be able to find that an object will stay at constant velocity when it has no net external force acting on it, which only occurs in our ideal computational model. And so we'll use the tracker model as well as the glow script computational model. And then we'll use the principles of Newton's first law, where an object will stay at rest and an object will stay in motion unless acted on by a net external force. And then Newton's second law is used to show that a net force will result in an acceleration. And then the momentum principle is used to update our velocity when we have a force applied over a time period. Then some assumptions we made are our object is a point mass system, so we don't have to account for its angular momentum. And then our initial velocity is going to be our average velocity for the first time interval. And then net external forces acting on the object equals 0, so our normal force will equal our force of gravity and friction can be ignored. So our initial conditions were our camera remained stationary, keeping the same frame of reference. Our marker was given a force to begin its motion, however position is not recorded until after the applied force has ended. And then our marker strictly moved horizontally, and this is shown in the video tracker model with a positive x direction axis at negative 178 degrees. And so the marker is our system, and it was given an initial velocity that table and error its surroundings. Friction from surroundings are assumed negligible, and the motion was recorded from above. Then using the tracker app, the position of the marker was recorded in 1/30th second time intervals through the length of the video. And then our glow script code, it used the initial position given by the tracker model and the initial velocity calculated from the tracker video, where change in x over change in t. And then our net force equals 0. And then we update our velocity using the momentum principle, and then we update our position with initial position plus velocity times change in t, and we increment the time by 1/30th of a second until 1.833 seconds. And so our model comparison, we have a displacement graph, which means our slope is our velocity, and they both have the same initial velocity and position. However, our glow script data maintains a constant slope, and our tracker data displays a gradually decreasing slope, as you can see by their widening distance from each other. And so we have different final positions, and there's minimal net force and acceleration for the tracker video, as shown by this change in slope. And we can look at the data here and see our time periods and our positions at the times. And so our reasoning and conclusions, we can see that because we used the position time graph to illustrate slope as velocity, therefore the same line would mean the same slope and velocity. However, we did not experience the same line. And so no net force acts on object, so no acceleration should occur. However, the observed situation does not experience a frictionless surface, so friction was interacting with the marker. So that changed its velocity. However, in the computational model, there was no force acting on it at all, so it did not experience acceleration, and therefore the velocity maintained consistent. And so the errors we had is the table is not a frictionless surface, therefore a system interacted with its surroundings and we had friction. And the marker is not actually a point mass system, therefore tracking the same position on the tracker every time interval was difficult. And then the marker does not roll perfectly straight, as it is has a little bit of a flared end, so we could have chosen a better object, and we could have chosen a better surface as well that was more slick or frictionless. And then our what if scenarios, and what does it mean? Changing the axes would change the magnitude, would make the magnitude of velocity stay the same while its direction changes. So if you made it negative x direction, it would be the exact same, just in the opposite direction. And you could make it in the y direction or at an angle, and the magnitude would still be the same. And then the forces acting on the observed object give a net force equal to 0, are the force of gravity and the normal force from the table. That's what gives it no movement in the y direction, and then it was assumed to have no force in the x direction. However, it did experience some friction.